Hi everybody, this is Eugene O'Loughlin and welcome to my series of short how-to videos. In this video we're going to learn how to perform an Anova post-hoc test in R. So when we conduct an analysis of variance, or Anova for short test, we are first of all testing, you can see in our null and alternative hypothesis here on lines 4 and lines 5, we're first of all testing the population means. Our null hypothesis is that the population means are equal, and the alternative hypothesis is that at least two of the population means are not equal. This is video number 90 in this series of videos on how to program in R, and in video number 89, the previous video, I walked through the process of working out how to perform an Anova test using some sample data. So I'm going to run very quickly through that here. So straight away on line 9 and line 10 I'm going to read in a data file. So this data file, 90, is number 90 CSV file. This is available in my GitHub, and you'll find a link to that in the information section beneath this video on the YouTube page. So let me read the file in and print the diet. It's diet data, it's fictitious data, and when I show this data here at the bottom, we can see that what we have here is we have in column, the first column is diet, so we have three diets, diets number 1, diet number 2, and diet number 3. We've got the weight of the people at the beginning of the diet program at week 1, and then we take their weight again after 8 weeks of diet, and we calculate then in the last column the weight loss. So what I want to do now is, in the Anova, is to see if there's a significant difference between the mean weight loss for diet 1 versus diet 2 versus diet 3. So let's go ahead and do that. First of all, let's visualize that. So I've got a box plot here, a simple box plot of all three diets, and on the right hand side you can see the three diets across the x-axis, and then the weight loss in kilograms on the y-axis. And we can see that diet 1 and diet 2 are very similar to each other. There's quite a lot of overlap. We can see that diet number 3 appears, at least visually, to the result is that there is more weight loss using diet number 3. So we have a suspicion that we will find a difference, but we need to conduct the Anova test to see if that difference is significant. Now, I also need to, in line 15 here, the diet variable, which is in the first column in the console here, that is those are integers, 1, 2, and 3. So in order to use those as factors or categorical variables, I need to coerce them to a factor. So that's what I'm doing here on line 15. And that then allows me to use this variable diet $data in my AOV function to calculate the Anova test. So I'm going to conduct on line 17 here. This is going to conduct the Anova test for me, and then using the summary function I can display the result of that test. And we can see lots of information here, but the two key pieces of information that we need are the F value, because that's useful in reporting. So that's 6.551, which is quite a large F value, but the most important value of all is the P value. This is a PR listed here of 0.00239, and we can see with the two asterisks here, it means that that is significantly, we have found a significant difference at the 0.01 or 1% level. So all this tells us is that we have at least two of the means are different. It's possible in our case we've got three diets, so it could be that all three are different from each other, or that only one is different from the other two, as we might suspect using the visualization here. So when we want to find out if the differences, so we have found a difference, we want to know where the differences are, and are those differences significant? And the way we do that is we use what's called the Tukey honest significant difference, Tukey HSD function. So I'm going to try that out here. HSD. And as always with a new function, if you haven't tried it before, go to the help screen and type in Tukey HSD, and you'll find some information on this in the help section of I should have a capital T there, sorry. Try that again. You get some information about how the test is run, a description of it, what arguments and parameters, and some examples and so on. So if you haven't used it before, please do that. And so what I'm going to do here is I have created my Anova test using the AOV function, and I've stored the resulting table in a vector called table. So all I need to do is run the Tukey test on that table. Okay, and press run. And that gives us some interesting information here. So I'm just going to move everything up so we can see both the Anova table and the code. So I've run this line of code here in line 20, and it's given me this output here. So this is a multiple comparisons table. And the last 3 lines in the output here are the most important ones. The numbers here in the first column, 2-1, 3-1, 3-2, they refer to the 3 diets, because that's what we've called them, 1, 2, and 3. And the first column after that then is the mean difference between the diets. So for example, the difference between the means of diet 2 and diet 1 is 0.379. The mean difference between diet 3 and diet 1 is 2.157, so that's quite a big mean difference. And the mean difference between diets 3 and diet 2 is 1.77 recurring. That's also quite a big difference between the means here. So we have very little difference between the means of 1 and 2, as we suspected if I could bring the plots back here. So there's very little difference between the means of diet 1 and diet 2, but we can see here that diet 3 is quite different from the others. The mean difference is biggest. So I'm going to jump past the lower and upper bounds here for a moment and take a look at the p. These are adjusted p-values for the Tukey test. And the first p-value, the difference between diet 2 and diet 1, that's 2 on the first line, the p-value is 0.827. That is not significant at an alpha value of 0.05. Therefore, there is no significant difference between diet 2 and diet 1, and we can see that visually as well as probably the case. Now, the difference between diet 3 and diet 1 has a p-value of 0.003. That is less than 0.0, or alpha value of 0.05. Therefore, we have found a significant difference between diet 3 and diet 1. It would appear that diet 3 has a significantly higher weight loss compared to diet number 1. And then the last line, this is the difference between diet 3 and diet number 2. The p-value is, in the last number here, is 0.0159, and that is also less than my alpha value of 0.05. Therefore, there's also a significant difference between diet 3 and diet 2. The lower and upper bounds here in the center of these outputs, these are the confidence intervals, so we want to be 95% confident that the true mean lies between these 2 bounds, and we can actually visualize that. So I'm going to go back up to the code here for a second. Visualize those differences using a simple plot function. Plot, and what I'm going to do is plot the contents of line 20 here. So just put that into the inverted commas and press run, and we get a difference in the mean levels of the 3 diets here. So we've got the mean here, so that value there that I'm pointing to, the difference between diet 2 and diet number 1 is in the top line. That mean value there, as we can see, the mean difference is 0.379, so that's the value there. The value in the center of this middle of the second line represents the differences between the means of 3 and diet 1. That's 2.159, so that's just above 2 there. And we can see that the third one, the mean difference between the means of 3 and 2 is 1.77, and we can see that where that position is on the x-axis. And then we've got our upper and lower bounds on that, so we can be 95% confident that the population mean differences lie between those 2 upper and lower values. So that's how you perform an analysis of variance post-hoc Tukey test. I hope you found this video useful. Thank you for your attention.